Good evening. Welcome to our Long Now talk with Sara Imari Walker. I'm Rebecca Lendl, Executive Director here at the Long Now Foundation. One of the things we really love about Long Now is our community. All of you here tonight and tuning in via the live stream. Before we dive in, we'd love to invite you all to check in with each other around a question that we might explore in tonight's program. So if you will, please turn to the person next to you and chat a little bit about the question, what is life? What is life? Wonderful, thank you. We'll gather back. We hope you'll continue these conversations following Sara's talk tonight. We'll gather in the lobby just outside the theater where we'll be pouring complimentary tastings of Long Now wine by Pellicero, a small family-run vineyard in Italy. I also want to express our deepest gratitude to the many thousands of supporters and members around the world. Many of you are here tonight who make Long Now's work possible. And a special thanks to Anthropic, our lead sponsor for this year's talks. Thank you. I'm excited to now introduce to you our guest host for the evening, Benjamin Bratton, director of the Antikythera program at the Berggruen Institute. Benjamin is a philosopher of technology and gave his own really fascinating Long Now talk back here in January, which I encourage you all to check out if you haven't already. It's one of my favorites. Benjamin and Sara are longtime collaborators, and they're working at the very edges of their respective disciplines. And we're fortunate to have them here with us tonight as kind of voyagers at these new frontiers of thought. Following Benjamin's introduction, we're going to watch a short film on long-term thinking. It's a tradition here we call our long short, and it will kind of help orient us to the adventure ahead. So thank you for being with us, and enjoy. And over to you, Benjamin Bratton.
Thanks, Rebecca. So I was very happy when Long Now asked me to introduce Sara, and then they said, we'd like you to introduce the work of Sara in 2 minutes, which, if you know Sara's work, is a bit difficult. I'm going to do my best. So what I imagine, sort of this, if there was sometime in the future a Sara Walker for Beginners book, what it might be about, what sort of the key concepts are on in this as well. And as you'll see, Sara's talk is going to be quite a wild ride. So what I sort of come up with is sort of like, let's say, some key concepts of Walkerism that if you can kind of hold on to, maybe in your mind all at once, this may help give you a little bit of a menu of what you're in store for. First, astrobiology. We generally think of astrobiology as like the Martians and stuff from outer space. No, it's also a way in which we think about us right here. We are the astrobiology. It's life in relationship to this. Second, selection, what we think of as natural selection, begins before biology. It's actually much deeper in time and deeper in process, which if you think about it, actually sort of changes everything. life, which is the main sort of the topic of Sara's work, is something that is different from being alive. Alive and life are actually different things, which she will explain in some detail. That life, as life evolves and accrues, it builds upon itself. It's all about scaffolds, and scaffolds building on scaffolds, and scaffolds building on scaffolds that becomes increasingly complex. The newest thing is actually the oldest thing, as Sara will explain. So the amount of complexity in something also speaks to the amount of time it took for this to evolve. The amount of time in something is the amount of complexity in it. And so the most complex things in our universe, like our technosphere, are actually the oldest things. Technologies, or the things that we call technologies, are themselves a form of life. They're not separate from life. They are a kind of life, and they are also a kind of life with which we think. We think through the technologies which allow us to see the world in a different way, which then allows us to remake the world in a different way. So once again, it's life making life all the way on down. What is the basic unit of life? Well, for some it was the cell. For Sara, it's the whole planet. It takes a planet to make what we recognize as life. All of the processes working together to come to constitute what we recognize in this form. And then lastly, to discover life is going to prove something that ultimately, I think in Walkerism, hasn't actually happened yet, will be more like discovering gravity than anything else. So those are sort of 8 key ideas. I know people are supposed to be able to like hold 7 numbers in your head all at one time, so I've given you 8. If you can manage to hold all of these in your head at once, this will give you a little bit of a starting point to what you're about to experience. With that, I'm very happy to introduce first the long short and then Sara Imari Walker. Thank you.
I'm so happy to see everyone here tonight. Thanks so much for coming out. I think we're going to have a very fun evening. I'm really excited to share some ideas with you. This is all a work in progress, and I want you to feel like you're on a part of the journey, because really what the research program is fundamentally about what we are as living things. And what I hope that we can do with the kind of work that we're doing is actually develop new languages to understand ourselves. And so when I'm thinking fundamentally about the nature of life, I think we don't understand it yet. It's a little bit like what Ben was saying in the introduction. It's like, think about how humans talked about gravity before we had an understanding of the theory of gravity, right? We couldn't understand planetary motion in the night sky as being the same as what's holding us here on Earth. And so I think we don't have the language to understand what life is. We don't understand ourselves. And so that's actually what we're trying to do. So the title of the talk is An Informational Theory for Life. And I started very early in my career thinking about information, but it's transformed quite a bit. So I'm going to kind of show you the current state of it. And it starts with this question: are we alone? I think probably most of us in this room hopefully have thought about this at least once. Not are we alone like as a person, but are we alone in the universe? And usually when we think about this question, we think about the immensity of space, all of the stars and galaxies out there. So the image in the background here is the Hubble Deep Field. And the Hubble Deep Field is a tiny image on the night sky as far as spatial volume, but it contains millions of galaxies, and each galaxy has billions of stars. And I've been told most of my career that surely life must be common in the universe because there's lots of territory for it to emerge. But the facts of the matter are that we only know this planet is inhabited, and we don't know if there's any life in any of those billions of galaxies out there. And I would like to know. I don't know about you guys. Would you guys like to know? Yes, we want to know. Okay, good. All right, I'm in the right crowd. All right, good. The curious lot is here. All right, fantastic. So how do we come to understand whether any of these stars, any of the planets that we found around stars in our own galaxy actually is inhabited? I think this is it's a good question for the long now, because I don't think it's a year-long problem for us. I don't think it's a decade-long problem. This is at least a century or millennia-long problem. We've been asking this question for a long time. And I'm hoping that our generation can get us closer. But currently, the way we understand the world is by actually collecting data from our telescopes and building simulations of that data. Right, so this is just a spatial map of the galaxies that I had in that picture. And in fact, when we start to model the universe and we try to understand it, we have kind of ways that we think about modeling and paradigms that we use that are centuries old in the way that we think about how the universe works. So this picture of the spatial map of the galaxy actually looks a little bit like this picture. This picture is a cellular automata. And so for those that might not know what a cellular automata is, it's a very simple computational model. And people in my field of complex systems, or one of the many fields I have worked in, that study emergent complexity, like to use these simple toy models because they display very complex dynamical patterns. So if I took this model and I actually ran it, this one particular one I'm showing is called the game of life. You might see a richness of the kind of patterns that are displayed, and this is just a very short clip, but you could go online after the talk if you're super curious and play with the game of life for hours. People have been discovering patterns in it for decades. It's actually really kind of an interesting niche culture. But what happens in this model is it's actually assuming a kind of dynamical system that Newton came up with originally when he was thinking about trying to understand motion in the physical world and mechanical laws of motion. And so what we do when we try to study the universe is we simulate it with our models. And the kinds of simulations we have currently assume some kind of initial condition and some fixed rule that governs the universe for all time. And so when we study emergent complexity in the game of life, we're assuming the rules never change. We're assuming nothing about the universe fundamentally changes because of the patterns in it. And this is not what we experience as living things. We've lived enough history as humans to know that our ideas, our culture, the things we do actually change the structure of the reality around us. And so this paradigm doesn't fit us anymore. We don't have the right paradigm for understanding the reality we actually live in. It's not the paradigm written 300 years ago in theoretical physics. And so the question that I'm interested in tonight, but just more fundamentally, since I've been working on the origin of life my entire career, is how does the knowledge of this particular problem transform this kind of fundamental level of understanding that we have about reality? And so we can think about the sort of models of the universe we built over the centuries. So this one is a model of the solar system. And this was derived over many centuries. It started, very early with epicycles and this idea of, trying to build predictive models of planetary motion, which were circles inside of circles. And you'll notice that my image here is not even accurate because they're not ellipses, but you imagine some kind of mechanism for the universe. And the reason we came up with this mechanistic model was because we invented clocks that could accurately keep track of time in seconds. And we used that technology to actually accurately map planetary motion. And then with that accurate map, we were able to realize that they were ellipses. Galileo actually figured out about inertia, and Newton came up with laws of gravitation. And so we had this model of the universe that came actually inspired by the idea of mechanical clocks in some sense, of the universe as a mechanism, a clockwork mechanism, with the laws of planetary motion. And interestingly, sort of a theme that you're going to see throughout the talk is that each new theory of physics we develop comes with its own concept of time. And the time we inherited from Newton's generation is that time is linear. It's a substance the universe moves through. If you notice planetary motion, we have laws. The laws remain fixed. And time is something that this system actually passes through. It's not an active property of the system. Later, we came up with the laws of thermodynamics, again, trying to look at the real world and understand it. We invented steam engines. We needed theories that actually helped us understand how they worked. This became thermodynamics, and we started to think about the universe as a giant engine. The second law of thermodynamics rules all, and time has a direction. The time as a direction is a little bit antithetical to the time as linear, and there's still discussions ongoing about that, but fundamentally what thermodynamics is telling us is that time is directional. And in the last century, we had sort of a new paradigm emerge, that the universe is a simulation. So this is sort of the popular zeitgeist that we're living in a computer simulation. And interestingly enough, there were actually two theories of relativity that emerged in the last century. The one that's familiar to most of us is the special theory of relativity and general relativity, which gave us the concept of relative time in physics. But there's a relative time in computation as well, which is the fact that the same program can run at different times on different computers. And so I think this idea of time as relative was just kind of an emergent cultural thing in many of our theories that emerged in the last century. Now, each of the models of the universe that emerged with the technologies of the time that I just showed you, I think still is in the same paradigm, that the universe doesn't fundamentally change over time and the rules are fixed. And interestingly enough, we have a theory that emerged in the 1800s as an explanation for biological forms, the theory of evolution, which Darwin is most famous for, but many other people were working on similar ideas, including his grandfather. And Darwin was a big fan of Newton's, and he actually, was really frustrated by the fact that we didn't have laws as simple as Newton's laws to describe life, but he still came up with very elegant theories and ideas about how to explain it. And the juxtaposition I want you to hold in your mind is this idea of fixed laws, fixed rules that govern our universe. The universe is predictable, deterministic, with this idea of endless forms. What does it really mean to have endless forms? Is that really possible in the universe as we understand it now? Is that really possible in the actual physical universe? And if the real universe can do endless forms, what would that kind of physics look like? Our planet seems to have that. So we're going to talk about the question, are we alone, for this evening? But we're going to talk about it as a lens of what are we? Because I think if we don't fundamentally understand ourselves and we don't understand how we're architecting our reality, we don't understand what we would look like from the outside, we're not going to be able to recognize things like us in the universe. We're not going to know what we're talking about because we don't have the languages to talk to each other about the phenomena of life. In fact, in my field, this is really funny. So sorry, I'm laughing already because I just remember being a postdoc and going to a conference at a chemistry meeting, and one of my colleagues stood up and said, life does not exist. And this was sort of the opening of their talk, and this is the culture of chemists working on the origin of life, is it's much easier to assume the phenomena of life doesn't exist than to tackle it head on. And in fact, there's similar things that, once you look at molecules, it's very clear life is not there, and you can just reduce everything to the parts of living things. But of course, there's also the paradox that no atom in your body is alive, yet you are alive as a living entity. And I don't know, how many people in here think they're alive? Okay, cool. All right, good. I didn't see any chairs raise their hands, but I saw most of the people. Okay, I think we're getting the categories moderately right. I personally felt deeply existentially perplexed. I would go to these meetings on origins of life, and almost no one was talking about the origin of life. They were talking about other problems. How do you make a protein or an amino acid, which is a component of a protein? Like, how do you make the parts of living things prebiotically? If we take everything apart about what we are and we try to engineer it in an experiment. And to me, as I think about it now, it's not how I understood it then. Basically, they're deconstructing 4 billion years of evolution, and they're using intelligent design to replace it. And this is not the question we need to ask. The question we need to ask is, how does the universe generate information and complexity when it has none? That is the origin of life. And I think that question has some really interesting consequences, which we're going to explore tonight. And one thing I want you to think about when I'm talking about the concepts is the idea that theories themselves are technologies. So one of the reasons I walk through these models of the universe is that each one has framed fundamentally how we think about ourselves and our place in the universe. And it's quite entertaining to me because sometimes I'll go places and people will tell me, they use the second law of thermodynamics to explain why they're a nihilist. Is it nihilist? Is this how you say this? Yes, thank you. I always have trouble with that word. So imagine using fundamental physics to inform your daily life philosophy. Now, it's not something everyone does, but some people do. And the reason I like picking on this example is even if theoretical physics and the ideas that come out of that exercise seem very esoteric to you and part of a small part of a community that has little to do with the daily workings of everyone else on the planet, these ideas percolate, and they are part of the sort of base layer of understanding of our reality, and they become part of human culture over time. And so I think we have a deep responsibility to actually cultivate theories as technologies that are actually enabling for the future. And that our theories themselves need to paint optimistic views about what we are and our place in the universe. They also need to actually correspond to reality, which is the hard part of being a physicist. But for me, science fundamentally, when you really think about science as a human endeavor, it's not about the experiment and the hypothesis testing. It's about building explanations for how the world works that last centuries. That's what we try to do as scientists at the base level of what we do. And all of the things that individual scientists do, we're trying to fill in that narrative. It's the narrative of reality that we want to tell ourselves. So I'm going to start talking now about life and the work that I'm doing with my collaborators. Metrology is a word that I've only run into recently. I like challenging myself by suddenly immersing myself in different fields, and metrology is the science of measurement. And you would think as a physicist I would have understood what a measurement was in my undergrad education. I can tell you I did not ever get a course in what a measurement is. And if you get into the science of measurement, it's incredibly complex. And so one of the ways I think about measurement right now is that measurement is the way that we take our abstract ideas and we try to map them actually to the physical world through devices that allow us to probe the world outside of our own mind and look for structural regularities. So measurement is actually incredibly important because it's how we map our abstraction to physical reality. And if your theory doesn't correspond to measurement or you can't embed your abstraction in a measurement, you have no way of testing it. And when I started working on the origin of life, when I was a PhD student, very reluctantly at first, actually, I'll have you know, I wanted to be a cosmologist. I thought that was very romantic. And then I realized, origins of life was something that no one had an idea about. Like, no one had any conceptual framing for this problem. And that actually became the love of my life, conceptually and intellectually, is this problem. Okay, so when I was working on it at that early stage, I thought we might be able to come up with theories, but we would never be able to test them. And it turns out there was someone else on the planet, Lee Cronin, who's a chemist, who was thinking about the same problem in a very different way than I was. And Lee's problem was that he didn't like the way that anyone was doing origin of life chemistry. Because of this issue of the amount of design we were putting into the experiments, we were looking for things that are on our planet now, molecular structures, and assuming that they were relevant to the origin of life as a general process in the universe, rather than looking for how unconstrained chemical systems generate complexity without any design put in by us or anything else. And so Lee is trying to build robots in his lab that can explore chemistry as messy as possible, the messier the better, because he wants to see life emerge in his lab. And he says, well, if life's gonna emerge in my lab, how will I measure it? And so this is actually the foundations of the theory that I'm gonna introduce to you. It's called assembly theory. And the conjecture of the theory is that life is the only mechanism the universe has for generating complexity. There are no Boltzmann brains, if you know that concept. We don't get fluctuating existence of objects like in this room. You will exist nowhere else in the universe. There's not a multiverse of possibilities. You only exist here, and you exist here because 4 billion years was necessary to construct you on this planet. That's the framing that we have. So it's very contrary to current physics, which has this idea that everything can exist everywhere. And there might be another you out there, but it's just a very low probability, or you might just be a brain that fluctuated into existence and your experience right now is not real. All of those things are not consistent with the paradigm that we're building. What we think is that complexity happens because of evolution and selection, and the space is so huge and the universe is small by comparison to all the things it could create that existence is really special. If you get to exist, you are like, that's amazing. Okay. So, yes, woo! What up for existence? All right, cool. I like this enthusiasm. I also like existing. It's great. It's better than the alternative. All right. So life is the only way to generate complex objects. And so how did this happen? Okay, so I just want to go through this argument. I just told you that you probably don't exist anywhere else. Great. I'm glad we're here. But what are we actually talking about? So I think when I show you the Hubble deep field, I think most of us have a sense that the universe is big, right? Because we're told it's huge. It's 13.7 billion light years across, and there's billions of galaxies out there. We don't actually think about how big the space of possibilities a single planet can generate. Combinatorial space, I'm going to talk about a lot. You can think about it as the space of all configurations of something. So I had to learn chemistry this way. But you can also think of Lego, or you can think of language, think of all possible ideas you could build with human language, or you can think about all possible technologies. You can think about all possible molecules. Combinatorial space is really big. It's actually uncountably big. So I'm going to give you an example of one molecule, and I borrowed this example from Lee, which is Taxol. So Taxol is a molecule that's been discovered on Earth. It's not a particularly special molecule. It's used as an anti-cancer drug. But if you wanted to make every version of a molecule, a three-dimensional structure that corresponds to the same molecular formula, and you had just one copy of each molecule, that one molecular formula would fill 1.5 universes of volume. One molecule. So actually, when cheminformaticians try to compute this number of possible molecules, they can't. We don't know how big chemical space is because we don't know how many possible molecules there are. And so this gets into an interesting question, because it's like, why does Taxol exist on this planet and not the other possibilities? Clearly, our universe doesn't have enough time and resources to make every single molecule with Taxol's molecular formula. It doesn't have enough resources to make every molecule with the same molecular formula as DNA. It doesn't have all the resources to make all the configurations of what could be the chairs in this room. it can't exhaust all possibilities. So this raises a fundamental question about what is the mechanism of what gets to exist. Why are these structures the ones that actually we observe as physical objects? And these other ones we might imagine, we might be able to say something about chemical space because we observe a molecule. So we have this idea of this counterfactual space that could exist, but we actually don't observe it to exist. The things we do exist, what our conjecture is they exist because evolution and selection have constrained that possibility space. There's information in the history that makes this object and not this object. And this is where we start to get into an actual way of building an informational theory of life. So to explain the idea, I'm going to start with Lego, because Lego's much easier for most of us than chemistry. Probably most of us maybe have had a pile in our home that looks like this if you have children or if you just like having fun. So if I was going to shake the Lego set indefinitely, what kind of structures do we expect to arise out of this? Exactly, okay. How long do I have? Okay. Can all of you hold an image in your mind of something you might build out of these Lego? Great. All right, I'm gonna also make something out of these Lego. How many of you made this? Just curious, I've never done this before. Did anyone make this object? No, okay. Oh, we got one. Oh, excellent, okay, cool. Probably, we already made this object because it's been imprinted on most of our minds. Most of you probably recognize it. It's a castle, at least. I hope most people know this is a castle. Okay, good. We do live in the same selected history. But this one's Hogwarts. Now, I think, did most of you make objects that were much simpler than this? How many people made something very simple? Okay, so even trying to make something like mentally as an exercise that's very complex is actually quite hard because it requires a lot of steps. And this is actually the way that we think about formalizing the complexity of an object. So I'm going to introduce assembly theory now, and I want you to think about the Lego analogy. But the idea is if you take something down to its parts, and you take the parts and you put them together, and then you keep doing that by putting parts together that you've built already, you will have a sequence of steps that's the shortest causal history for making that object. And we call that the assembly index, and this becomes how hard it is for the universe to produce that object. That's all you need to know about it. Castles are hard. They don't happen spontaneously. They require a lot of evolution. And in this case, it requires a lot of human evolution because we had to have cultural evolution. We had to build castles. We had to have somebody write a book about a little boy and magic that became wildly popular. And we also had to have Lego and billions of them on the planet. And then we get that. Okay, so that's not an easy object for the universe to construct. It requires a lot of history. Now we want to formalize that idea. How do you formalize this in an objective way, a way that you can actually do physics with? So this is where we get into the idea that there's a property, this minimal number of steps to produce an object. I'm showing it here now for ATP, which is a critical molecule in biology. For ATP, the minimum number of steps where you take bonds as fundamental units instead of Lego blocks, and you put the bonds together, and then you put the things you've made already to get ATP is 21 steps. Now I can compute that for a graph of the molecule once I understand the physics. But here's where what Lee did was really clever. He was in the lab, he was trying to build robots to explore for origins of life, and he said, I have a mass spectrometer. I can do measurements on molecules by breaking them apart and looking at the mass to charge ratio of the molecules and the fragments. If I can use this to probe how complex these structures are in a way that I can measure, then I can do something interesting. And so this is actually the genesis of assembly theory, was thought experiments on mass spec and the fragmentation that mass spec do to resolve the causal structure of molecules. And the exercise is that this process of breaking a molecule apart and trying to resolve the minimal steps to rebuild it from those elementary parts actually can be mapped to measurements in the lab, and actually Lee's lab has done it now with NMR and infrared and mass spec. So there's 3 different ways that you can measure the same property of molecules. And it allows you to say the minimal amount of causation, evolution, selection, information, whatever you want to call it. We don't have the words for these things, assembly index. Like we're trying to invent words for this molecule. Okay, so why is this important? Why is it important that we can measure this kind of constructed complexity or this causation? It's important because of this conjecture we had that life is the only thing in the universe that can build complex objects. So remember how big this space of Taxol is. Now, if you're in chemical space and you add a single bond, there's many ways you can do it. And so every time you add a single bond in those assembly steps, you're actually increasing the complexity in a space that's exponentially growing. So the space gets larger at every step that you take. So if you do an assembly index increase of 1, you've moved into an exponentially larger space every single step. So what we're measuring with this causal measure is actually this compression of selection into these objects that get to exist against this exponentially growing background. And our conjecture is because of the structure of that space, there should be a threshold that we should never expect to observe an object unless it's the product of life. That there was actually a selective mechanism, an information processing system. That was where we went into it. And so Lee's lab is very clever. So this is just sort of a depiction that you can take a certain number of steps and then suddenly you might have something that's alive, done for origami. The principles of assembly theory are quite general. They actually went and tested it in the lab. So this is a paper that was published in 2021. Building a life meter with this idea of molecular assembly. And so they went and they took a whole bunch of samples, abiotic, biological, dead. Someone got pissed off that beer is a signature of life. I don't know what that was about. But the conjecture actually held up to the experimental test. So what was done here is the molecular assembly that I just told you, the minimum number of steps is shown on the x-axis on this plot. For you guys, it's on the right, that says life. The only molecules that we found above assembly index 15 were products of life. So if you take abiotic samples, and actually NASA was really interested in this, so they sent samples to Lee's lab that they had blinded, and they really tried to trick him. They sent him samples of murchison, which is like one of the messiest chemistries that's abiotic. It's a meteorite, very messy. And what they were able to do is using this approach with the measurement techniques that they developed to be able to distinguish the biological from non-biological samples. And it conformed to the theory's conjecture that there should be a very abrupt complexity threshold and that living things were the only things that could produce things above this background. Because the space is getting so exponentially large, we should never observe those objects in high abundance enough to detect them. And if you go into pure abiotic samples like meteorites, what they are is what we call tar. They're just a total random mess of molecules. You can't actually even differentiate some of the molecules because there's just so much combinatorial complexity. And what life does is selected out specific structures in high abundance that are very complex. So we can measure that. That's pretty cool. It's very cool for me because as a theoretical physicist, I live in abstract land most of the time. Those of you that know me well know I'm a very, spacey person, I guess, in a good way. But what we're trying to do is actually look at this and use it now to build a theory. And one of the things that we're excited about is this idea of recognizing alien life as constructed complexity. So there's clear applications to looking for life on other worlds if we don't know the molecules. We can actually go in and we can discover life as we don't know it, even life as no one knows it. And that's exciting. But what I'm really after is that explanation for what we are, the fundamental physics of life. And I'm very excited about where assembly theory can take us with that. So what I want to get to now is using this fundamental idea of the kind of complexity assembly captures, this idea that there's a minimum number of causal steps to produce an object, and this somehow tells us about how hard it is for the universe to generate that structure. We can use it actually to formalize some really interesting theories and philosophies about the nature of life. And it's going to be a little bit counterintuitive. Most of the history of physics is. And so a lot of the ideas I'm going to talk about seem to be merging computation and material languages in a really weird way. And that's kind of on purpose, because I think what we're doing by taking these measurements that are of this causal structure, this kind of, some people might call it a computational structure of an object. I don't like to think about it that way, but you might. What we're really doing is doing a unification of the ideas of information as an abstract property and thinking about it now as a physical property. And if you look at the history of physics, every time we do one of these kind of unifications, it really changes our thinking. And so that's what I'm hoping is on the frontier here. So I'm going to talk about assembly space as if it's a physical space, because that's the way that I think about it. So we have invented many kinds of physical spaces in our history. One of them is coordinate space. And we invented that by inventing rulers and actually measuring the physical geometry of our environment. Assembly space, you can think of this idea of the assembly index actually measures things in this what seems to us to be an abstract space, but actually has become measurable through the advent of assembly theory of how causally deep objects are. And if we can measure that, then we can start to orient all of these complex objects in our world and root them in a physical space. And that's actually what we're trying to do. So I'm showing here an assembly space for adenosine. It's a molecule that's very important in genetic systems. And what I want you to take from this is that this idea of the assembly space is actually a material property. It's one we can measure. And we can also think of it as an informational property. Because what it's talking about, what it's capturing, is how much information and selection are in the history of that object in order for it to exist. So it's a physical space, you can measure it, it's predictive. What does it tell us about evolution and selection as fundamental mechanisms in our universe? So in the introduction, Ben also mentioned this idea of selection before biology. And so we're really after this idea that all the structures that the universe creates are selected to exist, and they might exist in a larger space. And so we have some objects we can observe. They might be molecules, they might be a Lego castle, and we can construct a space of this minimal causal history, the assembly space, what we call assembly observed. This space tells us a lot about the structure of what doesn't exist, which is super interesting. And this is where it gets into a really intriguing philosophy and theory of information. So I'll walk you through it very briefly and kind of quickly. We're in like the deep weeds of theoretical physics now. The first layer that you can build out of that space is, imagine I take all of the Lego blocks and I build every single possible structure, but I don't obey the rules of the Lego universe. I can glue them together. I don't have to use those little, I never know what these things are called, nubs or like whatever they are on the Legos. So I can build the space of all imaginable structures. Some of them are non-physical by the laws of the Lego universe. That's what we call assembly universe. It's an imagined space. So somehow encoded in these objects is actually our ability to, as intelligent agents, to extract this kind of space that it could exist, but it doesn't. The second layer is assembly possible, which includes all the structures that are actually possible to construct with the rules of that universe. And so for Lego, it would be actually using the building block brick rules to construct objects, not just assuming that they could stick together in arbitrary ways. In chemistry, it's using real chemical bonds and looking at thermodynamic stability. So there's a set of possible structures that are consistent with our laws of physics. Those would be consistent with standard physics also. But what assembly theory offers is a second layer inside of that. So this is kind of the third layer in the nested assembly universe, which we call assembly contingent, which is the observable structures that the universe actually can build because they're built along historically contingent trajectories. So this idea of the assembly space and looking at the structure as actually being a physical feature means when you're actually building an evolutionary system, it has to scaffold on the layers that came before. And because that space is so exponentially large, it can't exhaust every layer. So by the time you get to things like us, we are so historically contingent. If you rewound history 100 years, we would be radically different right now. Because the space is so exponentially large, it becomes unpredictable. So the real history we observe is just one such history within the structure. And our ability to access some of the other histories by looking at our own causal structure is actually one of the mechanisms I think that we use to create novelty in the future. We can learn the rules of our own history, and we can use them to actually build into the future. So we have a way of measuring how deep you are in this assembly space. We do it with this equation we call the assembly equation. It really only has two properties you need to worry about. It's exponential in the number of steps because that space is exponentially expanding, and it cares about how many copies you see of an object. The reason being, a one-off fluctuation doesn't imply a long lineage of things that actually could rebuild that object. So what we're interested in is the causation on a planet like us that can make many things that are similar in structure. So human beings are selected structures that exist on this planet. We're not exact copies, but there's many of us because evolution actually has a reliable mechanism for generating human-like structures. And so this equation is actually capturing that feature in this very abstract space and allowing us to figure out ways to measure this as a generic property of physical systems. Now, I mentioned this idea of a threshold in this exponentially expanding space. So this is how we formalize the origin of life. The origin of life is when things become too complex that a specific trajectory has to actually scaffold on itself in order to get to that level of complexity. It has to build a history and a memory. Selection has to happen. There has to be an information processing system that feeds back on itself recursively in order to construct into the future in this space. That's the origin of life. Otherwise, you get a combinatorial mess of exploring all possibilities, and our universe cannot do that for complex things because there are too many to exist all at once. So it has to make choices. This is very anthropocentric language. But this is why we get to exist and other things don't, because our entire history has led to our existence. And in fact, we are our history. That is the physical thing that is us. So the definition of life that I'll offer tonight is that life is lineages of propagating information. It's actually these causal histories accrued over many generations and actually physical in objects. And known physics exists down here. We don't know this transition point yet, but I think assembly theory is allowing us to get close. And the origin of life happens in chemistry originally. It's the first combinatorial space a planet generates where it can't exhaust all possibilities. And if you want to see complex structure, life has to emerge on a planet. And then the origin of life actually is a continual process that happens anytime a new combinatorial space is built. So I actually think the origin of life is a process that happens in languages and in technologies. It's a general process of generating novelty out of combinatorial spaces and then allowing complexity to emerge out of them. So this is the physics that we're after, is that actual process. You might be scratching your head. It's a little abstract. It was quite funny when our paper came out. We had a paper in Nature that was very deeply theoretical, which was like very exciting. I have never had a scientific paper go viral before. So this was my favorite meme. And that's the abstract of our paper, introducing the ideas of assembly theory. Obviously, he's very confused. You might be saying similar things. It's a lot of things that we folded in to really try to get at this problem of how life arises in the universe. So I think it's a complex set of topics. I want to talk for a few minutes before wrapping up about the idea of assembly theory as an existential technology, because I think one of the reasons that our paper was so confusing is the language didn't fit. We wrote the paper in what I felt like is a self-consistent language, and I remember these very deep arguments with Lee. I think we wrote 150 drafts of the paper with our collaborators, and it was very intense. The language, I think, was self-consistent, but we used words in ways that people weren't familiar with, and I think this is because it is a new idea, and we're trying to really pull a whole bunch of undercurrents and conceptual frameworks together and try to build a new language. And therefore, hopefully, it offers a new existential technology in the sense of the history of physics. So I already mentioned that new theories offer new concepts of time. Assembly theory has its own concept of time, which is time is material. Time is a property of objects in the sense that we're 4 billion years old. And you might say, I'm not allowed to invent new materials. I know some people that would beg to differ. Roger Penrose, Nobel laureate in physics, does not like the word material because it suggests we know what the material is. And Madonna lives in a material world. And I'm pretty sure social reality is equally real to elementary particles. And so I think if you look at the history of physics, the things we call matter are things we invented measurements for, and could embed abstract ideas in theories. So why is it we use mass and acceleration for understanding motion? It's because we could measure those things in a very regular way, and they happen to be the right measurements to actually build into our theories of motion. But it took us a long time to figure out what measurements map to the abstractions. And so inventing new material realities, I think, is something that's very consistent with the history of physics. Another concept, fundamental unit of life is not the cell, it's the lineage. And as I mentioned, you have parts of you that are 4 billion years old. So I have a friend, Michael Lockman, that if I ask him how old he is, he'll say he's 3.8 billion years old. Those are some of that's when we think the origin of life happened. He looks good for his age. You all also look great for your age. So the idea being that we have been constructed on this planet across 4 billion years, and the reason we're not reducible to our atoms, why that fundamental layer doesn't describe us, is because when we do that, we remove all of that time and causation. And that's actually where we exist. That's where the causal structure is that is us, is embedded in this history of time. And so I think to understand life, we have to think about time in a real physical way. And actually, evolved objects, one of the reasons they're so perplexing for us to see is because they're bigger in time than space. Imagine putting 4 billion years in this tiny volume of my brain, right? That's what we are, 4 billion years of constructed complexity inside a very small volume. I think this is one of the reasons that reality is looking increasingly virtual as we become increasingly complex, because most of the objects in our world are now deep in time, and our sense perception has evolved to interact with the spatial dimension, not the temporal dimension, right? And so the power of theoretical physics has always been to build abstractions that correspond to reality and allow us to see reality in new ways. And we didn't really understand gravity, we didn't understand the curvature of the space-time around us for most of our history, and I think we don't understand the causal structures that we're embedded in and actually just how deep they are. And so information looks like it hops around between physical materials because it's actually the structure that is embedded deep in time, and it's just around us everywhere. If you adopt this view, the largest known causal structure in the universe collectively is our technosphere. So if we looked at our universe in spatial volume, we look very small. But if we look at it in terms of causal time volume, our planet is huge. And in fact, I think right now on our planet, the largest density of causal volume per unit mass is the human brain. And this is one of the reasons that we can abstract so well. And we haven't manifested that yet in our technology, because the sort of causal structure is much more distributed in terms of energy per unit mass, et cetera. Okay. Endless form's most beautiful. The universe doesn't predict the future, it constructs it. What it does is predict the past. The future is undetermined till it happens. Why? Because in the complex universe we live, the volume of things we can create is much larger than what exists now. There's not enough information existing now to specify where we're going. We actually live in an undeterministic universe. I think that's completely consistent with quantum mechanics. That's a whole separate conversation. Okay. History and knowledge determine what's possible. So I'm showing two processes that are consistent with the laws of physics: launching satellites into space, building high atomic number elements. Both of those things can happen on our planet because of the knowledge that's been acquired over billions of years and then evolving intelligent systems like us that invent laws of physics that can launch satellites into space, something we don't see on any other planet, and can create elements that only exist here. All right, last thing I want to introduce, which is one of my favorite, is first contact in the lab. So we talk a lot about AI and alien right now, two concepts we don't understand. This is one of the reasons that I'm really interested in solving the origin of life. And most of the time when I say this, I go places and people are like, what are you talking about, Sarah? What does that even mean? I'm going to try to explain what I mean a little bit better than I have before. I'm hoping I'm getting there. But the idea is we actually want to understand how the universe constructs complexity, and we want to see that history. I want to see the causal structure underlying us. I want to understand what that physics is. So quantifying the ghost in the machine is, we see all of these things being animated in our environment right now. All of our technologies are coming alive, but we actually can't see the historical contingency that got there. We can trace information across genomes, but we can't trace information from genomic biology into technologies. But there's information transfer between those substrates, right? Our technologies are part of our lineage. And so we need to be able to actually see that underlying structure in order to understand how we're evolving and co-evolving with the technologies that we're creating. So I think we're not going to discover alien life on another planet first. I think we're going to discover it here on Earth first, hopefully, if we're successful, by building experiments to search chemical space for new life forms. The idea being, if we can do that, we can isolate the physics of that origin of life transition and really understand how is it that our universe crosses that threshold and starts to build information processing systems and constructed complexity. We're a tiny, tiny fragment of chemical space. This is the Earth's biosphere's complexity of chemistry, drawn as a single network, planetary chemistry. We exist somewhere in this giant space. There are probably other kinds of chemistry planets could generate, other kinds of living chemistry. So could we build experiments that can build entirely new lineages totally different from the one that emerged on Earth without putting the design in, without using ourselves as intelligent designers? We want to know how the universe designs itself. So we're trying to build experiments that allow searching for the origin of life in the lab and understanding the source of novelty and non-determinism underlying creation. I actually think there is no description of the universe from the outside. It's constructing itself, and we want to learn the rules of that. So first contact for me is an event. It's actually contact, like realizing we make a discovery of alien life, but more important is that first contact is an existential technology. And to conclude, I'm going to use this like very good in this crowd, about the sort of structure of the different layers that we all exist in. And part of my reason for this is I love fashion and I love theoretical physics, so it's the top and bottom layer. But I also really deeply think, as I mentioned before, that if we don't work on the base level of our understanding of reality, the entire structure starts to become incongruent. So I think this idea that we need new fundamental theoretical physics to understand the time that we're living in now and what life is and where we're going is critically important for this reason. And so with that, I'm going to thank my lab and my amazing collaborators and all of you. I went a little long, so I appreciate that. And thank you, guys. Thank you.
That was amazing.
Thanks.
It's always so fun to.
They're great.
Always so fun to listen to you. I always learn so much every time. So I have obviously a million questions. I'm going to try to keep it to maybe two.
Yeah, we live in a finite universe.
Finite universe, yes. I'm trying to keep it to maybe 2 or 3 as well. And then we've got some questions from the audience as well. We'll go through this as well. So hopefully these are sort of generative. Maybe sort of the technosphere and this really wonderful sort of paradox that actually turns out not to be a paradox after all, that the technosphere, which has this, as you put it, the largest causal structure embedded within it, which is usually thought of as sort of the newest thing, and this is actually the oldest thing in the universe because it has the most causal structure around it. And I wonder if you could talk a little bit about differentiate, or maybe it's the same thing, whether or not the causality, the sort of accumulated causation that has accrued over these billions of years that is embedded within this, that's one kind of causality. But now the technosphere itself is also causing things, right? It has a kind of agency, perhaps mindless agency, that can cause, that's able to do things that also previously couldn't be done. Is your mind, is there a kind of necessary symmetry between the amount of, let's say, involved causality that's in something and the amount of causal agency that thing might have?
Yes.
Okay, so we're going faster
Short
than I
answer.
thought.
Yeah, no, it was fun while you were talking, which
yeah.
often happens when I have conversations with you. I build really nice visuals in my head. So I think so they're absolutely related. So things that have the most causal power in the universe are things that are deep in time. But it's actually very interesting because most of the time you can actually act on your past history. So where your causal is the things that are behind you in time, and the things ahead of you are kind of this noisy horizon. So I don't think the technosphere will have a causal power of its own until there's a larger structure on it. So it's almost like it's post-selected.
Until there's a larger structure on it?
Yes.
In the future at some point?
Yes.
What would that be?
So we still have most of the causation. Does that make you happy or sad?
Both. I mean, I suppose.
Yeah.
What you also talked about this, you ended with saying that we are co-evolving.
Yes.
With our technologies, right?
Yes.
And that it's selecting on us and we're selecting on it, right, as well. So maybe it's both.
Yes.
Yep.
I mean, the whole system is being co-constructed.
For sure.
And so
including us.
Yes, including us. And so I think the question of agency is quite hard because
Yeah.
agency is very distributed.
For sure.
And it's also temporally distributed. So I think it's always interesting, like the place this also comes up is like in questions of free will, and there's like an issue about whether you have free will or not, but free will is a temporally distributed property, and it depends on the actual causal act that you're aiming to do. So, I couldn't be in Arizona right now because I'm in San Francisco, but I could be in Arizona tomorrow because I planned ahead, right? So your free will is distributed over time, and I think it's the same with these causal structures, that the actual causation they have is distributed in time. So it's recursively deep, but it's also, you can think about one structure, but it's many such interacting structures, and they're all layered.
Yeah.
Yeah.
That's clear to me anyway. I don't know if any of you.
I should have been an artist. It would have been much easier to communicate. Yeah.
One of the things that you've been working on lately is this idea of the perceptual horizon.
Yes.
Right. Which is, maybe I ask you to explain that a little bit more. As I understand it, it has to do with the ways in which, and this goes a bit to the history of science that you showed, that different technologies allow us to perceive the universe in different ways. And because we can perceive the universe in different ways, we can measure it in different ways. And this, in essence, both enables and constrains the kind of science that's possible, right? And so this horizon is expanding, right? And perhaps computational simulations are the latest version of this. But the idea is that this is not only changing, but in essence getting wider or getting bigger.
Yep.
And so I wanted to ask you to explain that a little bit more, but in the context of this question. You've said a number of times that you imagine that when you perhaps, you and Lee, discover what life really is, there'd be something more like the discovery of gravity. Will that only be possible because the perceptual horizon has expanded to such a degree that that level of conceptual granularity is possible?
Yeah. So let me explain for people that haven't heard me talk about that idea before, where it comes from. So I usually use atoms as an example, right? So when atoms as elements were discovered, we thought they were the base level of reality, right? So atom comes from the ancient Greek as a word, and when we discovered the atomic elements, we called them atoms because we thought they were the substance everything was made of. But subsequently, we developed technology that allowed us to see substructure in the atom. And right now, the sort of leading theory of a fundamental theory of physics is string theory. And the only reason that theory is not accepted right now is because we can't measure that deep into. So it's a technological hurdle to test ideas of that theory. And so this brings to the forefront this idea that the horizon of what we call fundamental actually evolves with our technology because it evolves with the way that we can actually measure and perceive the world. LIGO is another example. Gravitational waves have been permeating this planet for billions of years, but we took the invention of Einstein's general theory of relativity, and then LIGO to detect gravitational waves. Right? So we build all of these technologies to perceive the world in new ways, And this led me to think that the fundamental things are not at the horizon. They're all the constructed complexity in the horizon, because the way that we actually expand our ways of knowing, if we think about ourselves in this causal bubble, is by building new apparatus to explore the boundaries of our bubble. And so if we're doing that, we need to be large enough as a causal structure to see the things smaller than us. And I think this is the transition we're undergoing now, that technologies and animating more things as alive that we're doing now is going to fold back and allow us to understand what life is. Because we have to have a large enough horizon in order to see that physics. Right? So we can't, you can't understand patterns unless you've observed enough history. Right, so we don't even know the patterns in our own history and culture because human history hasn't been around long enough for us to actually see regularity there.
So, okay, so there's a question of, to come back to in a different way, so how you define the future in relationship to this. But what I'm sort of hearing you say is that technology is itself a form of life, but that in order, there would need to be this expansion of this horizon so that particular form of life can, in essence, recursively look back at itself. So the question I wanted to ask in this is, what would that technology be like? What might it be? And maybe you already answered part of this. What would be the preconditions to its appearance?
So I think this is why I was talking about theories as existential technologies, because I think what good theories do is they allow you to see the world in a new way, and that's actually the scaffold for embedding the measurements. So I see as one of the critical technologies the conceptual development of assembly theory, which is, a multi-collaborative effort. But also, I think some of them are going to be the actual instruments in the lab, and artificial intelligence to some extent as a tool for measurement. You got a question?
I got a few. I went to the office of there. Well, let me ask you then about the artificial intelligence, because it seems this is an area where there's a lot of already attention paid to a kind of co-evolutionary dynamic of this as well, and there's in many ways a lot of focus on the role of AI as a kind of collaborator within science, and you're sort of suggesting
I think
that
about them as more like a microscope. So if you're looking at structures that are so large, you need to be able to process the data and collate. Like it's like microscopes allow us to see tiny structures, and telescopes allow us to see distant structures. Artificial intelligence algorithms allow us to see large patterns, like the periphery of very large causal structures, but just the surface layer. And so I think the idea of having a theory that allows us to understand the historical contingency that gets to these very large complex systems is the other piece of it. So assembly theory to me is the underlying architecture of how you get to this data layer that we exist in now, and AI is the technology of seeing that data layer.
Yeah, I like that. Let me then, we have a bit of time. I'd like to go to the questions from the audience.
Okay.
If that's okay, this as well. And some of them are, there's a pattern in here as well. I'm detecting.
Great.
So, which is probably good.
Must be a product of selection.
I think so, yes. This also goes to a little bit, this will lead to the question about the future, because I think I know where you're going to go.
It hasn't happened yet.
As far as we know. Right? I knew you were going to say that.
I'm so predictable.
Anticipatory.
Anticipatory.
Yeah. What is the role of mind in assembly theory?
Yeah, this is something I've thought a lot about, and Lee and I have talked a lot about, and also with our groups. But and Lee and I go back and forth about this a lot. I think minds are very deep in assembly space. So I think like the examples I like to give are things like perfect circles. Perfect circles are objects that can't exist as physical structures in the world, right? Because you can't have infinite precision to make them perfect. But they're an idea that exists in our minds. So I think what this suggests is there's a lot of, I talked about this idea of the virtualization of reality. I think there's a lot of the space that exists in this kind of virtual causal structure that actually can't be physical objects on their own, but they can exist
in a virtual,
in that virtual causal space and time. Like, I mean, time as a space. Sorry, not physical, not coordinate space, but like, this combinatorial space. And so I think what's interesting about minds is because of this very large depth in time and the ability to reach into those very abstract layers, there's much more things that we can manipulate about our environment and much more creativity we can induce in the world because we have access to these internally very large causal spaces. So to me, our ability to abstract is just evidence of how deep in time we are.
And those abstractions, though, they're kind of idealizations. You give the example of the circle, but you would differentiate that, I believe. I mean, perhaps mathematics would count as one of these abstractions. You would differentiate this from Neoplatonism.
Yes.
Where the followers of Neo-Plato.
Right. So yeah, I'm not a Platonist. I like Platonists. I have an allergic reaction to Platonism. I don't know what it is. I'm literally allergic to it intellectually. The reason being, I don't I think it's much more constructive, and this is probably the materialist in me, and I'm not sure if it's the Madonna or Penrose version of the materialist, because both are juxtaposed in my mind. But it's. To me, reality is great, and there's no reason with thinking that anything exists more than what exists here. And I think if we fold all of that in and we really think about the things in our mind and these abstract ideas we have as physical features of our reality and not in some imagined reality out there, it tells us much more about what's actually happening. And so the way that I think about abstractions is I want to know what the abstractions themselves are as physical architectures.
Right.
And so mathematics to me is particularly interesting because mathematics is supposed to be a universal language. And it corresponds to a lot of objects in the world. But really what it is like our mind's ability to actually causally influence the future because of the kind of patterns that exist in our own architecture. And so I see math as not, and science actually generally not as predictive but as constructive, as I mentioned in the talk, that these things that we do are actually part of the mechanism of how our planet is generating possibilities and moving into the future. And I think that's actually much more helpful because it gives us a lot of agency and control over things and a lot more understanding about us fundamentally than assuming there's some reality out there that we don't have access to, yet that reality is somehow supervening on us and controlling it.
And this is also what I think corresponds with your insistence about the materiality of information.
Yes.
Isn't it right? This is not this is a real thing.
I mean, if it kicks, it's real. I don't think there's anybody in this room that doubts that information is influencing their life. I think there's no sense to think that these things are not physical.
Yeah. Okay, this goes a little bit to this relationship between assembly theory and philosophy of science. Once again, what are the falsifiable predictions that assembly theory can make?
So one of them is that you could have arbitrarily high complexity objects happen outside of an evolutionary process, and so far we haven't observed that. So we don't observe, cell phones spontaneously fluctuating into existence on Mars, for example. They exist on our planet. That would be counter to assembly theory. I also think, one of the tests that Lee and I have been talking about is the idea that there's a minimal construction time for any object. And so, Lee's a brilliant experimentalist. I think if anybody could figure out how to do it, he would, but it's a tough problem. But if you could devise an experiment to actually demonstrate that something can't fluctuate into existence and it requires some history. So what would that experiment be? But I also think it's, in some sense, we get asked a lot about experimental tests, and I think there are many that we will devise, just like gravity has many tests. But there's also this idea of explanations, right? And so gravity is a language that we now use to describe this regularity of why we're stuck to our chairs, but it's also something our ancestors observed and their ancestors observed. And so I think there are deep things we know about the world and we don't have languages for. And I think assembly theory is a language for this deep regularity. And so in some sense, I don't know how you test an explanation that seems obvious. Do you see what I mean? It's a hard thing to do. And so you can test the sort of features of the mathematical theory and if it fits. But I also really believe that this deep layer of what science is doing is building better explanations, and the explanations are what carry us forward. And so I don't know what to do with that. I think science is much more varied than people traditionally. I really like this idea of epistemological anarchy in science.
Paul Feyerabend.
Yeah.
Okay, here's an experiment for you. Mass spectrometry may help measure assembly index for molecules, but how do you measure more complex or abstract forms of quote-unquote life, like a technology or a culture?
So the challenge we have with assembly theory right now is we think the theory is quite general, but developing it for new substrates to test the principles is quite hard. So we've done it for two in a rigorous way so far. One is molecules, and the second one is crystal materials like minerals and silicon chips. And so there you can tell the difference between a natural mineral and a technologically engineered mineral, which we call silicon, in a very precise way in assembly theory. But the challenge we have is this idea of assembly index has to be embedded in a measurement scheme. So you have to have some way of actually deconstructing what you think the causation in the object is, not your model of the causation, but how the universe actually generates that structure in terms of what causal constraints, what laws of physics are at play. And you have to be able to look at that as a substrate specific property. And then you need to be able, so once you can build the assembly space for the material, then you can apply assembly theory. But the assembly space is very non-trivial. Because and this is where assembly theory, I think, fundamentally differs from computation, because computation is like we can build computational models for everything, but there's one assembly space for a particular selective mechanism. And so the universe might be a self-constructing system, and all of these spaces have, that it builds all these causal spaces have different sets of laws and constraints in them and different kinds of contingency, and assembly spaces can be nested in other assembly spaces. And so I think what we need to do is to demonstrate it in enough materials to show that life is a general phenomena. That's what I'm interested in, actually.
So I think the question is also about things that you would call real and physical, like a culture.
Yep.
But aren't necessarily material in the same sort of way. And so the question is that how, like, presumably some cultures are more, like some languages are more complex than other languages.
But the question becomes hard, right? So which substrate do you use for constructing the assembly space of language? Do you use vocalization? Do you use written word? Do you use what's actually imprinted in computers? And so without actually understanding the architecture of how these things are embedded in the substrate, like we don't know what they are. So I think, I think like language, for example, like people think we understand language. Language is a set of patterns that some entities on this planet utter to other entities on the planet, right? Like, so if we're looking at that as an objective thing outside of ourselves and asking what is that as a physical causal structure, it's a highly non-trivial problem. And so I think it's possible, but I don't want to give you easy answers to it because I think it's a really hard challenge.
Yeah, fair enough. One of the ways in which you also sort of talk about this relationship between assembly, correct me if I'm wrong, this relationship between assembly theory and, let's say, the artificialization of life, so what we call synthetic biology or life, is that there's a kind of, another recursive process is that sort of through the artificialization process, we begin to discover what the thing is that is being artificialized. Is that a fair conjecture in terms of where you see?
Can you explain what you mean? I'm not following.
Well, I'm thinking about this in relationship to your idea that alien life will be discovered in the lab.
Yes.
Right?
Oh, I see.
Presumably, it's not just because it happened to show up on a university campus one day. That's why it's discovered in the lab. But rather because there's a process that's set up, perhaps to reconstruct life, or perhaps something about it that will result in this thing that we will, in essence, the way I think, sort of retroactively understand. Yes. Like, aha, this thing actually is life. So it might not be new, right? But it's still like the realization is new. Is that? Please.
No, but I think
Yeah.
actually what this revealed is there's a slightly different use of the word artificialization, or like a distinction I want to make.
Please.
Because so artificialization to me is like when humans build large language models, and there's clear informational lineage from us into the technology. Whereas the origin of life, the way that we talk about it, is you want to pinch off as much of that lineage as possible in the experiment.
Right.
So
That's right.
So it's actually the process of trying to remove the artificialization as much as possible, because you want to know how the universe does it de novo. And I think until we can do that, we actually won't know how much of the continuity is between us and machines, for example. Because we actually don't know what the universe can generate de novo in a substrate in the absence of a lineage.
There's a whole nother thread, but I want to get to some other questions around this as well. And we're sort of at the end of time, so there's two questions that I think are quite related to each other, and I think might be an interesting place to end on. Can there be other if there are other substrates on which life can form, are there be other substrates that can hold minds? And the other question, which is probably related to this, which is phrased in an interesting way, when is AI life?
Okay, these are both good.
When is an interesting way of putting that?
So I think any substrate that has enough combinatorial richness, kind of an open-ended, maybe an uncomputable one. So I talked about the fact that all possible molecules are actually not computable. Like we don't have enough resources in the entire planet to generate all of chemical space in a model. There are some, so those are the ones that I think are interesting because they're capable of open-ended complexity. I think that's actually the one that we're interested with respect to life.
Yeah.
Now, one place that we've applied assembly theory, actually there's one other substrate I didn't mention, which is an atmosphere. So molecules, minerals, and atmospheres, I think we're pretty confident on. Atmospheres because we're interested in life detection on exoplanets. And atmospheres are kind of interesting because they're not combinatorially rich. There's about 16,000 volatile molecules that probably could be in an atmosphere, so it's a really small space. And so I think if you look at the transition to life in an exoplanet atmosphere, the sort of selection constraints you see are very weak. So I think we can pick up signatures of it, but it's not this very sharp transition. So I think living worlds, in terms of the imprint of selection in their atmosphere, are on kind of a continuum with non-living worlds. But I think there's still a transition we can pick up. But substrates that have very deep combinatorial rich structure can enter an open-ended cascade. Those are the things that we would really call living. Again, distinction between life and living.
Yeah.
And the ones that are like very deep structures in that space can have minds. And I think AI is shallow right now. But I think the integrated structure of our technologies on this planet is getting deeper. But any particular model, to me, is still a very shallow system. Again, it goes back to this idea of, like, are you processing the data at the outer periphery, which I think is what we're doing right now, or are you building structures that are deep? And so it's very unclear to me about how the predictive algorithms are they things that we're interacting with and we're seeing them as being causally deep because we're deep, but the actual embedding of that in the physical architecture might be still quite shallow.
But
So that's the question: is are they experiencing? Are they like what is the reality of a silicon chip processing a large language model? You don't want to ask about the output, right? The output is what we read on a screen. It's a predictive.
You mean, like, what is it like to be a chip?
What is it like to be a large language model embedded in a physical architecture? I don't think any of us know what that is.
No, I don't think any of us do know what it is. But presumably on the depth question, that if it is essentially something that we have made, we've sort of invested our depth in this in one way with part of the technosphere, that there would be a lot of evolutionary time embedded in these large models. Like
you put a lot of time in a small space, but most of that time is just the linguistic component right now, or certain kinds of structure of the path. Just to use LLMs as an example, because they're easy.
Evolution of language in that regard.
That's right.
That's right. Yeah.
So and I think the thing that's interesting to me is the interaction with words, right? So
words are shifting meaning all the time. And if I asked everybody, well, we did ask this, what is life? Like, there were probably as many different answers for that as there are people in the room, right? So the fact that there's a predictive correlation between that word and other words doesn't necessarily capture all the conceptual foundations underneath it. And so I think, again, it goes back to the causal richness of the history, and how we actually build meaning is mostly about our physical architecture, not these predictive associations of words.
Yes.
Which is why we have disinformation issues and all these other things, because you have people with radically different causal histories interacting, and the words mean totally different things, and they're trying to like cloud each other's perceptions of reality.
Yeah.
And it's really easy to do with the surface layer if you're not seeing the structure underneath, if you're not seeing the experience of an individual. You can assume they have bad intentions when they don't.
Yeah, I mean, there's a whole other discussion about spatial AI around knowledge, which has to do with more sort of embedded knowledge, but that's be another talk. We need to sort of wrap it up here.
Yes.
And I just want to, first of all, say thank you on behalf of the whole audience for this such a rich body of ideas to think with as assembly theory, as a scaffold for many things that come next. And sort of thanks for this.
Cool.
Thanks for your time.
Yeah.
Thank you.